Dielectrics and polarization. As stated earlier, insulators are effectively the mere opposites of conductors. The charges inside a dielectric do not move around, since there are no free electrons. Electrons must then, not electrons, that's a wrong statement. Charges in dielectrics must redistribute themselves by shifting their center of charges. This is called polarization. This is the main characteristic of dielectrics or insulators. So here's what I'm thinking about as a main picture for you to think about. And what we find here is that this is Feynman's model. So here is Feynman's. Oops, I spelled that wrong. Model of a dielectric. And the way you want to think about this here is that you could imagine that we have concrete. So this whole thing here is concrete. And what we know about concrete here is that when we think about concrete, we know that concrete is set and does not allow movement. So to think about this in a slightly different way here, now imagine that we have holes in the concrete. Now what we're going to do here is that we're going to fill these holes with a conductor. And so what you're seeing in this situation here is that the holes are filled with conductors, which we could then induce charges on them. But the fact is that these holes cannot move. So when I think about an insulator, if I bring a charge, these conductors are then going to be induced. But we don't say the word induced, even though people use it very freely. And even I will say that I induced a charge on a dielectric. Technically, we try to separate those two and call it polarization. So that's the model that I want you to think about. I mean, it's a toy model, but nonetheless, it's effective in how we visualize this. So now let's get to it. Okay, so start with a single neutral atom. Where the charge distribution is symmetric. And that's important here. So what do I mean by charge that is symmetric? This means the centers of positive and negative charges are located at the center of, of the atom. Now, that's turns out to be quite important. So what I'm imagining here is that I have this. I have a volume that contains, the atom here. And in this atom here, what we find here is that sometimes you'll hear people call it a probability, distribution. Sometimes they say that, they have lots of words for it, or a cloud, an electron cloud. That's what I'm thinking right here. So what I'm thinking right here is that this here is the electron distribution. And that means that we have probability of finding the electron over there around here. Now, I'm going to say that that's the center of the electron cloud, the green cloud. But now we have a nucleus. So if I have a nucleus here, then right on top of that is the center of that nucleus here. And those two centers line up. This, when you have this, this is what we say is a uniformly, not uniformly, it's a uniform charge distribution. And that's because those two center of charges are right on top of each other. Now, here's what happens next. A nearby charge is brought close to this neutral atom. And these electron distributions are highly distortable. As a result, it becomes asymmetric. That is, these centers of charge have shifted by a tiny distance. And I mean tiny. It's a very, very, very tiny thing. So what am I doing here? So I have my atom, neutral atom. Okay, so it's right here. And then what I'm going to do here is that I'm going to come in here and I'm going to bring a charged rod. So in other words, I have a rod that's going to look like this. Let's say that this is a yellow rod. And so what I'm seeing here is that this rod now is negatively charged. So what does it do here? What it does here is that it distorts the atom. So all of a sudden, instead of it being circular, I now have an asymmetric shape here. So again, I still have my electron distribution, my probability function, but now the centers have shifted. So what I'm seeing here is that over here, I have my positive charge. And then over here, more of the electrons are going to be on this other side here. So this becomes negatively charged. So what you're seeing here is that this is the nucleus has shifted a tiny bit. And then right here, this is the highest probability of locating the electron. Because of this, it's not uniform. This is a non-uniform charge distribution. And this is the important piece. This process is called polarization. And in electric dipole, we typically call it a dipole moment, which I'll get more into this later, is created. Once again, the key point here is that dielectric materials are capable of distorting the electron distribution, but no motion occurs. So now let's start talking about our system here. So what I'm going to do here is that I'm going to take this guy right here, and I'm going to bring here. And now what we want to do here is that we want to bring a charge rod to a dielectric. So I have a charge rod right here. And what I'm going to do is that I'm going to now say that suppose a charged rod is brought near a neutral dielectric. In other words, we could do this with wood, or we could pick plastic. There's lots of dielectrics that we could do. Now, here's what I imagined here. So now I have this guy here, and let me draw let's say it's this big. And so look how I'm drawing my gray here, because in my mind, I'm thinking concrete, and it's not going to let these atoms move here. So this guy is a neutral dielectric. And what I mean by neutral here is that I could form an atom. And what I mean by neutral is that I have symmetric charges. Okay, I have symmetric charges. So that means their center of masses is going to be right here. So now let's go put this guy in. So I'm going to copy this, and then I'm going to just start pasting. So I'm going to say there's right here. I'm going to move this in here. So let's say that I make my atom 6 atoms thick. Ideally, they would be symmetric. Doesn't look like it's going to be symmetric, but that's the breaks. And then one more, and then we get here. So now I have my dielectric right there. So now what do? I create dipoles. So if I create dipoles, that means I'm looking at something like this here. So now I'm going to get a shift in their center of masses. So what I'm thinking is that they're not circular anymore, but they're something like this. And so I'm only going to focus on their center of mass. So there's that center of mass, and then there's this center of mass right here. And we see that this is positive and negative. So now I'm going to come in here, and I'm going to start moving these in. Okay, last one. And then now you see that I have formed dipoles. This is what we call a polarized dielectric. So one of the things that we want to do is that I want to focus on a couple of things. And this is what we're seeing here. So I'm going to focus on the polarized dielectric. And sketch an effective model. So there's a couple of things that you should try to think about here. Now remember, if I was to look at the overall charges, it is still neutral. And what I mean by this is that I want you to think about the following picture here. Now, what I'm going to do is that I'm going to come in with my blue. And if I look at the inside, like this, what you're finding here is that what happens to these charges is that I end up creating a surface charge. So if I'm looking at this dielectric, if I look at the surface on the left side, what I find here is that I have surface charges. And this is what we call positive. So this guy right here, we say has been polarized positive. On the other hand, you could see the green ones, they would be right at the surface. Because remember, there's atoms at the surface. This is negatively charged. And so then we would say that this is polarized negative. So what about the inside? Start counting the atoms. If we have a uniform distribution, that's an idealized situation. If you start counting what's inside of here, look what we find here. We can see here that there are 1, 2, 3, 4. There are 4 positive charges, and there are 4 negative charges. So therefore, this is 0 inside. So when we look at a dielectric, that's exactly what we're seeing right there. We are seeing that there's this surface charge that comes about. So what I'd like to do is that I want to go back to the applet of a FET, and we want to go back and look at this thing here for a brief moment here. So let me set up, and then let's go. So what I'm going to do is that I'm going to look at FET, and I'm going to look at FET electrostatics app, and I'm going to look at the balloon and wall. So let's go look at that thing, and let me share my screen with you. And here's what we're seeing. So the first thing that I want to look at is that look at the balloon here. See how that thing it's neutral. It's not affected because it's not charged. Now, if I rub it up against the sweater, this thing is negatively charged. So look what happens here. It's going to go right towards the sweater. I don't care about the sweater. Just showing you that it's negatively charged. So now look at what happens when I bring it over to the wall. Look at what happens to the blue charges. You see how they're redistributing themselves? So there's a separation between the positive and negative charge centers. That's what's creating this guy right here. So now let me go back and show you what do I have here. So if I'm looking at what we just did, I took some screenshots and here's what we found. I find here that I have, these are neutral balloon and wall. Then what I did here is that this guy here, right? So now what we say here is that this is a negatively charged balloon. And what you're seeing here is that you are now polarizing the wall. So for example, you could see here is that you could see that there's a shift right here, right? There's a shift right here. There's a shift. There's a shift right here. And I'm guessing that this is a shift right in here like this. So you're seeing that these guys are shifting. Now note, I did not do that in the picture, but these guys are all shifting their center of charges in order to get polarized. So now the wall is polarized.